So here's our block sitting on top of our slab, and there's the force that's pulling the block to the left. Part of the thing that makes this problem awkward is that everything's going to the left instead of going to the right, but we'll deal with it. So they want to know what the accelerations are of the block and the slab. Now it's possible that the two accelerations are the same. That would be true if and only if this force was smaller than the static friction force. If this force is bigger than the static friction force, then this block is going to come loose from the slab and it's going to accelerate separately. So first let's find out what the static friction force would be. So let's look at the free body diagram of the block. So we have mass of the block times gravity. We have a normal force on the block. We have this force here going to the left, the pulling force, and we know what that is. And we have friction force going to the right. And let's say that's static friction, maybe. So if that was true, then the X equation would say minus F plus the static friction would be equal to 0, maybe. Okay? The Y equation would say normal force on the block minus mass of the block times gravity equals 0. What we're really interested in is what is the maximum value of the static friction, which happens when static friction is equal to mu sub static times normal force. Well, this equation tells us that the normal force on the block is equal to the mass of the block times gravity. So I can plug that in there. And so my static friction is going to be mu static mass of the block times gravity. And if you plug the numbers in here and calculate, I think you'll find that the static friction is less than the value of this force, which means they are not stuck together, they're actually moving separately. So this guy is moving faster and the slab on the bottom is moving slower. They have separate accelerations. So let's start over and draw our free body diagrams now, knowing that the block and the slab are going to accelerate separately. So for the block, it looks pretty much like what we had before. Mass of the block times gravity, normal force on the block, we have this force moving it to the left, and we have friction to the right, and now we know that this friction is kinetic friction. Now for the slab, we have mass of the slab times gravity. We have the normal force on the slab, but then we have to think about how the block is affecting the slab. Well, the block is pushing down on the slab because of its weight, and that's another way to say that is that this normal force on the block is actually coming from the slab. So we need to put normal force on the block pointing downward. Now, this friction on the slab, friction on the block, what's slowing the block down is the fact that the block is kind of moving the slab forward, which is to the left, right? So this frictional force that was on the block is on the slab also. Because it's happening right here, it affects both of them, right? If it's to the right for the block, it has to be to the left for the slab. So now we can write our equations. In the x direction for the block, friction minus the pushing force is going to be equal to what's happening. And we know the block is accelerating to the left. I'm going to go minus, because it's to the left, mass of the block times acceleration of the block. In the y direction, this is the same as before, normal force of the block minus mass of the block times gravity is equal to 0. And we know that this friction is mu sub k, the sliding friction coefficient, times the normal force on the block. And you can see that the normal force on the block is going to be equal to mass of the block times gravity, just like before. So my friction is going to be equal to mu sub k, sliding friction coefficient, mass of the block times gravity. I think that's going to be useful later. Now we're going to look over here. In the x direction for the slab, we have minus the frictional force is equal to, see that's the only thing in the x direction. So that has to be equal to minus mass of the slab times the acceleration of the slab. We know that the slab is accelerating to the left, so we know it's negative, and it has a different acceleration from the block. And we could just take those minus signs off. The y equation, normal force on the slab minus mass of the slab times gravity equals 0. I'm not going to write anything about friction underneath the slab because there is no friction down there. They said that, so we don't have to do that. So the two questions are to find this acceleration right here and to find this acceleration over there. Well, this one here looks really easy. The friction over here says we found that the friction is equal to this, mu sub k, mass of the block times gravity. I'm going to put that in here. Mu sub k, mass of the block times gravity, is equal to mass of the slab times the acceleration of the slab. So that means the acceleration of the slab is just sliding friction coefficient, which they gave us, the mass of the block, which we have, times gravity, divided by mass of the slab. And then to find the acceleration of the block, we look at this equation. We know everything in here except for the friction, and the friction is this. So I can rewrite this. I'll use another color. Instead of F, I'm going to write mu sub k, mass of the block, times gravity. That's friction. Minus the pushing force is equal to minus mass of the block, acceleration of the block. And I can solve that. Acceleration of the block is equal to the pushing force minus the friction, that's mu sub k, over mass of the block. And there you go.